Welcome back to the deep dive. Today, we're tackling multicollinearity in regression analysis.
hmm
You asked for a clearer picture of this challenge you run into when trying to figure out how different factors, well, influence an outcome.
Yeah, it's a common one.
So our mission today is to really unpack it. What is it?
Right.
Why does it matter? And crucially, what can we actually do about it based on the stuff you sent over?
Exactly. Regression is all about isolating effects, right? Seeing what each individual thing does.
Right.
But multicollinearity, well, it's like all those factors are tangled up, makes it really hard to see who's doing what.
Okay, so let's start there. What is it, technically?
Okay, so simply put, it's when your predictor variables, the things you're using to predict your outcome are highly correlated with each other.
Oh, okay, they're moving together.
Precisely.
Hmm.
And we usually talk about two types. There's perfect multicollinear, like an exact mathematical relationship, rare but breaks the math. And then there's imperfect multicollinearity. That's the more common one. It's a strong link, but not, perfectly predictable.
Okay, strong but not perfect.
Mm.
So how do you even spot this in your data? How do you know what's happening?
Good question. The main tool we use is called the variance inflation factor, the VIF.
VIF.
Yeah, basically you calculate a VIF for each predictor. A high VIF tells you that variable is strongly correlated with some combination of the other predictors in the model.
And what counts as high? Is there a magic number?
Well, there's no single strict cutoff,
Right.
but rules of thumb exist. Often people start getting concerned with VIFs over 5. Definitely over 10 is usually seen as a red flag.
Okay, VIFs over 5 or 10. Got it. So
Yeah.
why is that actually a problem? What does it do to the analysis?
Right, this is the key bit. Multicollinearity makes the estimates for your individual predictors, those regression coefficients, the slopes, it makes them unstable, unreliable.
Unstable.
Oh.
How so?
Think of it like trying to figure out how much salt versus how much pepper affected a dish's flavor when you always add them together in the same ratio.
Ah, okay. Hard to separate their individual effects.
Exactly. The model struggles to isolate the unique contribution of each predictor. So even really small changes in your data set, like adding or removing a few observations, can cause those coefficient estimates to swing wildly.
Wow. Okay, so the numbers you get back might not be trustworthy for individual predictors.
Precisely. Which really messes with interpretation, right?
Yeah, how so?
Well, if two predictors, say x1 and x2, are highly correlated and you see an effect, the model has a hard time telling you if it's really x1 causing the change or x2 or some mix.
So you can't confidently say increasing this specific variable leads to that change.
It becomes much harder to say that with confidence. Your interpretation of individual predictor importance gets, well, muddy. You might even find a variable that should be significant shows up as not significant.
Because its effect is sort of being masked or confused with another variable's effect.
You got it. And that also ties into hypothesis testing.
How does it affect the stats tests, like p-values?
Yeah. Because the model is uncertain about the individual coefficients, the standard errors associated with those coefficients get inflated. They get bigger.
Okay, bigger standard errors.
And bigger standard errors means smaller key statistics, which means larger p-values. So it becomes harder to reject the null hypothesis.
Meaning it's harder to conclude that a predictor actually has a statistically significant effect, even if it truly does.
Exactly. You might miss real relationships just because your predictors are too tangled up.
Okay, this is clearly a problem. What can we actually do about it? The sources mentioned some approaches.
Yeah, there are several strategies. One is ridge regression.
A ridge, yeah.
It's a technique that adds a tiny amount of bias to the coefficient estimates. It seems counterintuitive, adding bias.
Right.
But this little nudge actually helps to stabilize the estimates, making them less sensitive to the multicollinearity. It sort of shrinks them a bit, but makes them more reliable overall.
Interesting. Okay, what else? Principal component regression, PCR, was mentioned.
Right. PCR is a bit different. It takes your original set of correlated predictors and mathematically transforms them into a new set of variables called principal components.
Okay.
These components are, by design, uncorrelated with each other, and they capture most of the information from the original predictors. Then you run your regression using these components instead.
So you sidestep the correlation issue by using these new uncorrelated variables.
Essentially, yes.
And the simplest approach mentioned was just dropping one of the correlated variables.
That's often considered. If two variables are highly correlated, maybe you only need one of them in the model.
Seems straightforward. Any downsides?
Oh, definitely. It's a trade-off. Dropping a variable reduces multicollinearity, sure. But what if that variable is theoretically really important for your explanation?
Right, you might lose important information or make your model less interpretable from a subject matter perspective.
Exactly. It's not always the best solution, depends heavily on the context and your research goals.
Makes sense. Now, one last thing. Does this mostly apply to standard linear regression, or do we see similar issues in, say, nonlinear models like logistic regression?
That's a great point. While the classic definition involves linear correlation, the underlying problem, highly interdependent predictors making it hard to isolate effects, can absolutely show up in nonlinear models too.
Wow.
Even if the relationship isn't strictly linear, if predictors tend to move together or provide redundant information, you can still get unstable coefficients and interpretation challenges in models like logistic regression. The core issue of disentangling influences persists.
Okay, good to know it's not just a linear regression thing. All right, let's try and wrap this up. Key takeaways from this deep dive.
Well, multicollinearity boils down to high correlation between your predictors.
Right. And this leads to unstable coefficient estimates, making it tough to interpret the individual impact of each variable.
Yep. And it messes with hypothesis testing bigger standard errors, harder to find significant results.
We can spot it using VIF values.
Variance inflation factor.
And potential fixes include things like ridge regression, principal component regression, or sometimes carefully dropping a variable.
Each with its own pros and cons, of course.
Okay. So maybe a final thought for you, the listener.
Yeah, I think it's fascinating to step back and consider how often things we think are independent in the real world are actually tangled up together.
That's true, like income and education, maybe,
Yeah.
or diet and exercise habits.
Exactly. So the thought to leave you with is, how might these hidden interdependencies be complicating our understanding of cause and effect everywhere, not just in formal models? Thinking about how to spot and maybe account for these connections could lead to, well, much clearer and more robust insights.
A lot to think about there. Thanks for joining us on the deep dive.